Right now, in a clean room in Oregon, a machine the size of a bus and as heavy as 2 jets is firing lasers at droplets of molten tin 50,000 times a second. Each pulse explodes the tin into a plasma far hotter than the surface of the sun. And from that violence comes light just 13.5 nanometers wide, fine enough to carve features into silicon smaller than almost anything humans make by hand. That machine costs $380 million. Only one company on Earth can build it. And the 2 giants betting their futures on it, ASML, which makes it, and Intel, which staked its survival on being first to use it, may have bet right before the rules change. Because a completely different way of building chips is leaving the laboratory. It does not fire lasers. It does not need the machine. It lets the chip build itself. Let's start with the 2 ways to draw a circuit. For 60 years, there has been one way to make a chip, from the top down. Shine light through a stencil, etch where it lands, make the light finer to draw finer lines. That single idea built the digital world. And the company that perfected it, the Dutch firm ASML, now holds something almost unheard of. Not a lead, a monopoly. It is the only company on the planet that can build an extreme ultraviolet machine. Nikon tried. Canon tried. Both walked away. Every advanced chip in your phone, your laptop, and every AI data center on Earth was patterned by an ASML machine. No second supplier, no backup. But there's a second, stranger idea most people have never heard of. What if you didn't draw the pattern at all? What if you put the right chemistry on the wafer and let the molecules arrange themselves, the way oil and water separate on their own? That's directed self-assembly, or DSA. It uses molecules called block copolymers that naturally split into incredibly fine stripes and dots, features under 10 nanometers, with no expensive light at all. For decades, it was a defect-prone curiosity. Researchers at NIST, the University of Chicago, and the Belgian lab IMEC kept refining it. And in the last few years, it crossed a line. It started working. To see why that's a threat, you first have to understand the flaw inside ASML's machine. Here's what the marketing skips. The newest light is a victim of its own precision. To draw smaller features, ASML switched to a wavelength of just 13.5 nanometers. But the shorter the wavelength, the fewer photons you get for a given power. At that scale, you are working with so few photons, the process behaves like rolling dice. Engineers call it photon shot noise. Picture spray painting a straight line with only a handful of droplets instead of a smooth stream, some land left, some right, and the edge comes out ragged. That raggedness is line edge roughness, and it creates random failures called stochastic defects that get worse the smaller you go. IMEC even has a name for the trap, the stochastic cliffs. Push too small, and yields fall off the edge. This is the wall the whole industry is hitting, and exactly where the bottom-up idea turns dangerous. Block copolymers don't care about photon noise. When they self-assemble, chemistry forces them into clean, evenly spaced patterns, and they will repair a defective pattern the light left behind. At IMEC, researchers showed DSA could heal EUV's stochastic defects up to 3 line widths across in about 3 minutes. The cheap chemical process fixes the mistakes of the most expensive machine ever built. There's even a granted US patent describing how conventional EUV suffers from roughness and bridging defects below a 32 nanometer pitch, and how self-assembly cleans it up. The implication is staggering. If chemistry can rescue a cheaper exposure, maybe you don't need the most expensive light at all. Which brings us to the $380 million question. ASML's answer to the wall is a bigger machine, high NaEUV, wider optics, sharper features, and 8 nanometer resolution in a single shot, versus 13 nanometers. a genuine marvel. It also costs around $380 million, more than double the last generation, and weighs as much as 2 airliners. And here, the cracks show. In June 2026, TSMC, the most advanced chipmaker in the world, effectively called the machine too expensive and chose to delay High-NA for years, leaning on cheaper tools and clever patterning instead. The next generation, Hyper-NA, is projected to top $700 million per machine. The cost curve is going vertical. Now look at who said yes: Intel. It bet its entire comeback on being first to High-NA, taking the very first machine into its Oregon fab and building its make-or-break 14A process around it. Intel needs this to work. Its share of the leading edge slid into the single digits, and its outside customer foundry revenue is a sliver of TSMC's, hundreds of millions of dollars against tens of billions of dollars. Intel is spending hundreds of millions of dollars per machine to leapfrog a rival, just as a bottom-up technology hints the whole arms race might be optional. If self-assembly delivers fine patterns by complementing cheaper lithography, the core pitch of the $380 million machine that you must buy the priciest light starts to wobble. But money is only half the story. The other half is power. Here's why governments are watching, not just engineers. ASML's monopoly isn't only a business advantage, it is a weapon. Since 2019, the United States and its allies have used that single choke point to wage a technology war on China. The logic is ruthless. Only one company makes extreme ultraviolet machines, and it sits inside an alliance Washington can pressure, so you forbid it from selling its best tools to Beijing. Without extreme ultraviolet, the argument goes, China cannot build the most advanced AI chips. As the American Enterprise Institute laid out in a 2026 report, lithography acceptable is the single most concentrated choke point in the entire chip supply chain, which is exactly why it became the pressure point. For now, the wall mostly holds. Cut off from extreme ultraviolet, Chinese fabs run the same wafer through older deep ultraviolet machines 4 times over, and it is slow, costly, and error-prone, with yields reported around a third. But think about what self-assembly is. It is a way to reach finer patterns through chemistry and physics, with molecules arranging themselves instead of relying on a single band machine. It runs on materials, not on a $380 million tool inside an export-controlled alliance. You cannot put a custom stamp on the laws of chemistry. And it is no accident that some of the most ambitious self-assembly research has been funded directly by Chinese national science programs. If a mature bottom-up process ever lets a country stretch its existing, unrestricted machines into extreme ultraviolet territory, the wall does not fall, it quietly leaks. So what does this mean? Not that ASML is finished, it is not. Not that self-assembly replaces lithography tomorrow. Today, it mostly complements lithography and still faces real obstacles, especially the software, to run it at scale. The truth is subtler. For 60 years, whoever controlled the light controlled the chips. One company, one machine, one choke point held up your phone, your car, every AI model, and the balance of power between superpowers. Self-assembly is the first real crack in that idea. A hint that the future of computing may be decided not by who owns the most expensive machine, but by who masters the cheapest chemistry. You now understand something most investors and policymakers have not grasped. The next great battle in tech may be fought from the bottom up. The question was never whether this changes. The question is who controls it when it does.